So let us see how to evaluate this integral log x whole square. So
Okay, sir.
first of all, you will take this as, since you see only a one single function here, log x whole square, you will take log x whole square into 1, and function 1 you will take this as your second function. Log x you will take as your first function, because even by isolate, if you see, then the L come before A. So that is why log x whole square you will take as your first function. Integral 1 dx means simply dx minus integral derivative of twice log x. And what is the derivative? Dx of log x whole square into the integral of dx, and whole thing integrated as dx. So here integral dx you will get simply as x. So x log x whole square you are getting here, minus integral of derivative of log x whole square. Derivative of log x whole square is twice log x. Okay. Into the ddx of log x means 1 by x. So this is the derivative of log x. And integral dx is x dx. So what happens here? This and this they cancel. So what you simply get is x log x whole square minus, now you can take 2 out, integral log x dx. Okay. Next, x log x whole square remains as it is, minus twice. Now how do you integrate log x? Same by parts. Okay. Take log x as your first function, 1 is your second function, minus integral of derivative of the first into the integral of the second. Let's put a first bracket here. And this whole thing has to be within dx. So this now becomes x log x whole square minus twice x log x. This becomes x log x minus, in derivative of, this is integral of derivative of log x is 1 by x, and integral of dx is x dx. Okay, so this becomes x log x whole square minus twice of um, x log x minus integral dx. So this becomes x log x whole square minus twice x log x minus x plus c. Okay, this is your required integral. If you want, you can just simplify this a little. X log x whole square, and you can take x common to get 2x into log x minus 1 plus c. That's it. Okay,
Okay, sir.
let's see the next one. Now, just
Okay,
a
sir.
note small here. How will you evaluate this integral? Integral log x to the base 10. Natural log, you know how to evaluate. How will you evaluate this integral if the base is 10? See that you can write this integral as change of base formula. You can write this as log x by log 10, right?
Yes, sir.
Yes, sir.
Now log 10 is a constant. Remember, log 10 is not 1 because the base here is e for both, right?
Yes, sir. Yes, sir.
So 1
Yes,
by
sir.
log 10 you can take out, and this becomes integral log x dx simply. Now log x dx you can integrate by parts very easily.
Yes, sir.
Okay, so there's another important integral that we are going to discuss here. This is a very important integral actually. Um, uh, Integral here is log x plus root over x square plus a square, e square plus x square dx. Okay, this is your question. Okay, now this looks like a very difficult sum, but actually it is a very easy sum, because if you take log x, this can be written as 1 into log x plus square root a square plus x square dx. The main thing here is differentiation. If you know your differentiation well, you can do this integral very easily. Although this looks like a tough one. Now what you do here is you take log of x plus root over of a square plus x square as your first function. You take this as your first function into the integral of dx minus integral of the derivative of, let's put it in box brackets, derivative of log x plus root a square plus x square, okay, into the integral of dx and whole thing within dx. Now the next step is, say integral dx will be simply x, so you write this as x log x plus root a square plus x square minus integral of, what is the derivative of, now here the main differentiation is there. This differentiation if you can do, then it becomes a very easy sum if you can do this differentiation correctly. Okay, so how do you do this differentiation? First you differentiate log to get 1 by x plus root over e square plus x square. Now you differentiate whatever is within the log, and what is within the log? You have x plus root over of a square plus a square. So ddx of x plus root over of a square plus x square is 1 plus, if you differentiate the root, you will get 1 by 2 root
1 by 2 root under a
a
square
square
plus
plus x
x
square.
square.
Okay, and then you differentiate what is within the root
Yes, sir,
into
into 2x.
2x. Okay, if you can pull off this differentiation, then it becomes a very easy sum, and whole thing dx. So this and this they cancel. So what you get is x
Okay.
log. That is why repeatedly from the beginning I have been telling you, be thorough with your differentiation. Differentiation, if you know differentiation, you know everything. If you don't know differentiation, you don't know anything. 1 by x plus root over of a square plus x square. And here if you take the LCM, what do you get? You get root over of a square plus x square plus x. In the numerator, if you take the LCM, in the denominator, you simply get root over of a square plus x square, right? Um,
Yes, sir.
Yes,
um, into all this
sir,
in
into x.
into x
X.
dx. Now what happens?
Yes, sir.
This one and this one they cancel off. Okay, this and this they
Yes.
cancel off. So what you ultimately get here is x log x plus root over of e square minus x square minus integral. You simply get this integral x by root over of a square plus x square. That's it. And if you can evaluate this integral, then you can do, then the sum is done. How will you evaluate this integral? Can you tell me? Let us call this I1 and let us evaluate I1 separately. How will you evaluate this integral? Root over of x a square plus x square. Now see that if I differentiate a square plus x square, what do I get? I get 2x, right? Already have x in the
Yes, sir.
numerator. Okay, so what I do is I put t is equal to a square plus x square. So what happens? If I differentiate, I get dt dx is equal to 2x dx, right? That means I get
Yes, sir.
x dx is equal to half dt, isn't it?
Yes, sir.
Yes, sir.
I get x dx is equal to half dt. So now put it here. Your x dx you already have here. This becomes your half dt. So this becomes integral half dt divided by root over of a square plus x square is root t. Okay, so this is now if you take
Okay, sir.
half outside, you get integral dt by root t. And you know that root t can be written as t to the power of minus half plus c you can write is equal to, or you can write plus c later, not now. Once I remove the integral, then you can write plus c. So half, you can write this as t to the power of minus half plus 1 by minus half plus 1. So you get what? Half into 2. 1 minus half is half, which comes on top. It becomes 2 t to the power of half. So you get plus c. So what does it become? This becomes root over of a square plus x square plus c. So I1 is nothing but a square plus x square plus c. So therefore, what is I? Hence, I is equal to x log x plus root a square minus x square minus I1. And what is the value of I1 that we have got here? X log,
root under x a
Root
square. Oh, yes,
a
sir.
square plus x square plus c
this is plus x square plus
plus c.
root
Plus
over of a square plus x square. And you can give a c or you can give a k, whatever. Okay, just a different constant of integration because we are integrating twice. Okay, so that is what. But just give a constant. Okay, whether you give a c, whether you give a k, but definitely don't forget to give us constant.
okay, sir.
So that is what. Next, the next part of the problem that I would like to discuss is what if the integral is a square of an inverse circular function? Then what will you do? Sin inverse x whole square. What if you are given to evaluate this kind of an integral? In this kind of an integral, this is a square of an inverse circular function. So there no need to panic. What you'd simply do is you take sin inverse x whole square as your first function. You can write this as sin inverse x whole square into 1 dx. And you take sin inverse x whole square as your first function, 1 as your second function, minus integral of derivative of sin inverse x whole square, okay, into the integral of 1 dx and whole thing within dx. So this becomes x sin inverse x whole square minus integral of derivative of sin inverse x whole square is twice sin inverse x into the ddx of sin inverse x, which is root 1 minus x square into x dx. So this clearly becomes what? X sin inverse x
Yes, sir. Root under 1 more x square.
minus integral 2x sin inverse x divided by root 1 minus x square dx. Now you know that the derivative of 1 minus x square is minus 2x, right? And in the numerator, can you see a minus 2x there? You can see.
No, sir.
No, sir.
Hmm?
Minus 2x.
Um,
So
this
minus
one
2x
in
is not there. Plus 2 is there.
plus 2 I gave. Which one I gave? Uh, I can see a 2x there. Twice sin inverse x by root 1 minus x square into x. Yes, this is okay. What is your question? Tell me what you want to know. Tell me fast, fast. What do you want to know? Any confusion there? Let us call
Hello.
this. Yes. Tell me.
Yes, sir. Plus 2 is there, no?
Any confusion with the differentiation?
No,
No,
sir.
sir.
Okay. So the question is, how do I evaluate this integral? Okay. Let us take this as I1
Okay, sir.
and evaluate it separately. Now, this is a very important integral that you must know, where I1 is equal to integral 2x sine inverse x divided by root 1 minus x square dx. Now here you know that the derivative of sine inverse x is uh, you know that the derivative of sine inverse x is 1 by root 1 minus x square, right? So what you do is you
Yes,
put
sir.
t is equal to sine inverse x. Okay, that means if t is equal to sine inverse x, that means x is equal to sine t, right? So therefore, what do you get here? Dt dx is equal to 1 by root 1 minus x square. Am I right or not?
Yes, sir.
That means what do you get? Dt is equal to dx by root 1 minus x square, right? So let us put it here. Now dx by root 1 minus x square, you have got it here. This entire thing becomes your dt. Okay. So what is left here? Integral twice. Now what is x here? X is sine t. So put it here, sine t. Okay. And what is sine inverse x? Sine inverse x is t. Okay, dt. So
Yes,
that's
sir.
it. That's it.
Yes, sir.
So what you do
Yes,
is
sir.
this becomes integral twice integral t sine t dt. Very important integral. We will do 2 or 3 kinds of integral this way. After substitution, it becomes a integration by parts. So this is a combination. The example that I'm showing you is actually a combination of substitution and integration by parts. Okay. So this now
Okay, sir.
t sine t. How do you evaluate t sine t? Again by parts. Take t as your uh, which this t is your algebraic function and sine t is your trigonometric function. You can take mm, your algebraic function as your first function. Okay. So what you do is you write this as t integral sine t dt minus integral of ddt of t, derivative of the first function, into the integral of sine t dt, whole thing within dt. So t sine t, what is the integration of sine t? It is minus cos t. So minus t cos t minus integral of derivative ddt of t is 1 and integral of sine t is minus cos t. So this becomes a plus cos t dt. So this becomes minus t cos t, right? And integral of cos t is sine
Yes,
t
sir.
plus c. Now we want
Thank
to
you.
change everything in terms of x, because what have we
X.
substituted? We have substituted x is equal to x is t is equal to sine inverse x, or x is equal to sine t. So clearly this sine t, this one is x,
Thank you.
this one is x. But what about this? This is cos t. Now you see that if x is equal to, note here, let me write a note here, t is equal to sine t, right? T is
Yes,
equal to
sir.
Yes,
x is equal to sine t. Sorry, yes, x is equal to sine t. Here x is equal to sine t. That means what should be cos t? Cos t should be root over of 1 minus sine square t, which
Yes,
is
sir.
root 1 minus x square.
yes, sir.
Now you can put the values. Therefore, what is I1? I1 is minus t cos t plus sine t plus c. Now what is t here? T here is sine inverse x, right? So put sine inverse x
Yes, sir.
minus sine
Tan
inverse x.
inverse of x,
And what is cos t we have found
then
out? Root 1 minus x square.
yes, sir. 1 root under 1
And
minus x square.
sine t is x
T
simply
is x
plus c. So my
plus
answer
c.
here, so I1 here is root 1 minus x square minus, in fact, minus root 1 minus x square sine inverse x plus c. Okay, this is what I1. Hence, what is I? What was my I here? I here was x sin inverse whole square minus I1. X sin
Yes, sir.
inverse x whole square minus I1. And this is x sin inverse x whole square. Now there was a t, I think I forgot, my omitted that t. There were two here. Sorry, there was a two here, right? So I think I should write this two here. Yeah. So this becomes minus 2t plus 2. Okay, so this becomes minus 2t plus 2. So this becomes um, minus 2t plus 2. So this becomes 2, and here I have to write a 2 again. So that means this becomes 2 root and this becomes 2x. So therefore, if I write this here, it becomes minus 2 root 1 minus x square sin inverse x plus 2x. Okay. And constant of integration, you can put it as k here in the ultimate step. So here you have, what is your answer? X sin inverse x whole square plus, if you open the brackets, this becomes 2 root 1 minus x square sin inverse x minus 2x plus k. That is your answer. Okay, so this was in fact, the evaluation of
Okay, sir.
I1 was important here because this kind of integral we are going to deal with later on. After this, maybe I'll be doing this kind of where there is a combination of substitution and by parts. You first substitute something, okay, change the variable and then apply by parts. So let's see another example from a combination of substitution and by parts. Okay, let's see a combination of this. Question is, we'll start with this one. Let I is equal to integral sin inverse 2x by 1 plus x square. Okay, dx.
Yes, sir.
And let me make it a definite integral. Let us give limits 0 to 1. It does not matter. Okay, but still we can evaluate very easily. But as it is we have to evaluate as an indefinite integral first, and then we'll evaluate it as a definite integral. Okay, so what you do here is you write this as uh, let let us evaluate the indefinite integral first. Let I1 is equal to integral sin inverse 2x by 1 plus x square. Okay, dx. Okay, now what you do here
Yes,
is
sir.
Yes, sir.
you know the formula that sine 2 theta is 2 tan theta by 1 plus tan square theta. So let us put x is equal to tan theta. Okay, so that means what happens? Dx d theta becomes what? Sec square theta, right? That
Yes, sir.
means dx becomes sec square theta d theta, right? So let us now put it.
Yes,
Therefore, what does I1 become? I1 becomes integral sin inverse x, sin inverse 2 tan theta by 1 plus tan square theta. Okay. And dx, instead of dx, you put it as sec square theta d theta. So everything from x we have converted to theta.
yes,
So now this becomes sin inverse. Now you know that 2 tan theta by 1 plus tan square theta is sine 2 theta into sec square theta d theta. So what does this become? This simply becomes 2 theta. Sin inverse of sine 2 theta is simply 2 theta.
2 theta.
theta sec square theta d theta. Now this has to be integrated by parts.
No,
So hmm,
divided by 1 plus tan square theta, no?
which one? What?
Sir, the integral of sine inverse of sine to theta sec square theta divided by 1 plus tan square theta, it will be.
Huh? What is the problem? I could not understand.
Sir, it is not written 1 plus tan square theta. This
Tan square theta.
okay, sir. You have applied the formula.
And that is what I'm saying.
Yes, sir.
Now this has to be integrated by parts. Okay. This has to be integrated by
Yes, sir.
parts. So twice, which one? Theta sec square theta. Theta is an algebraic function. Sec square theta is a trigonometric function. So you take theta as your first function. Theta uh, integral sec square theta d theta minus integral of derivative of theta d theta of theta, okay, into the integral of sec square theta d theta, and whole thing should be within d theta. Okay,
Okay,
so
sir.
this is
Yes, sir.
twice. Now you know that integration sec square theta is tan theta, so this becomes theta tan theta, right, minus integral of derivative of d theta of theta is simply 1, and the integral of sec square theta is tan theta d theta. Okay, so this becomes
Yes,
Yes,
sir.
sir.
twice of theta tan theta minus integral of tan theta is log sec theta, right? Standard integral log sec theta.
Yes, sir. Yes, sir.
Now you change everything in terms of x. What had I assumed? I had assumed x is equal to tan theta. So let's write a note here. Note here x is equal to tan theta. Okay, that means theta must be equal to tan inverse x, right? So and here we also have a sec theta. So you know that sec square theta is equal to 1 plus tan square theta.
Yes, sir.
1 plus
Yes,
x
sir.
square. That means what is sec theta? Sec theta is square root of 1 plus x square, right? So therefore you can write it here. Therefore what is I1? I1 here is I1 here is twice of twice of theta tan theta. Tan theta is x and theta is tan inverse x. So x tan inverse x, right?
Yes, sir.
Minus
Yes, sir.
log sec theta. Log of sec theta we found root 1 plus x square. Log root 1 plus x square.
Root
Everything has
1
been
plus
changed
x
in
square.
terms of c. Okay. Now what you do here is you can simplify a little further. You can write this as twice x tan inverse x minus log root. You can write this as half log 1 plus x square. You can write or not,
Yes, sir.
Yes, sir. Into 2x.
because there is a square root. So that is why you can write this as half. Okay, put it in work within curly
Sir,
brackets
into
plus
2x.
into
2x. Sir, root under 1 plus x square is there. That's why.
yes. Now you can multiply by 2 throughout. You get 2x tan inverse x minus log 1 plus
Sir, half into 2 will cancel.
yes, okay, plus c. Right now we had to evaluate a definite integral. So let us go back to the definite integral. So what was I? Therefore I is equal to integral 0 to 1 sin inverse 2x by 1 plus x square dx. And what have we evaluated the indefinite integral as? We have evaluated the indefinite integral as 2x tan inverse x minus log 1 plus x square. You don't need to write the constant of integration, or you can write also, no problem, because as it is the constant of integral, it cancels in case of definite integral. Okay. So
Yes, sir.
now put the upper limit first. 2 into 1 into tan inverse 1 minus log 1 plus 1 square, right? This. Now put the lower limit, 2 into 0 into tan inverse 0 minus log 1 plus 0 square. So this entire thing actually becomes a 0. So what are you left with? You're left with only 2 tan inverse 1 minus log 2, right?
Yes, sir.
And
Yes,
tan
sir.
inverse 1 you know is pi by 4 minus log 2. So ultimately you get simply pi by 2 minus, that is your answer. Clear?
Yes, sir.
When we'll be doing definite integral, we'll see that this actually can be done in 2 lines. We did so much. We substituted, then we did by parts, then we applied the fundamental theorem of integral calculus. All this you can escape. Once you know the properties of definite integral, you can do this integral in 2 lines actually. Okay. So be doing the properties very soon once we finish with this chapter on integration by parts. Okay. And the next problem that I intend to do here is from IC again. This is at I is equal to integral 0 to pi cos 2x log sin x. Again, this problem can be done very easily with the help of definite integral. But since we are doing by parts, we'll do this by definite integral here. Okay. So 0 to pi. So let us evaluate this as an indefinite integral first. Let I1 is equal to integral cos 2x log sin x dx, right? So consider your cos 2x as this is a product of what? Trigonometric function and log function. So log function has to be the first function. Log sin x integral by Euler rule, log function has to be the first function. Minus integral of derivative of log sin x. I'll differentiate this directly. What is derivative of log sin x? It is cot x. Okay, cot x. Okay, into the integral of cos 2x whole cos 2x dx and whole thing within a dx. Okay, so this one
Yes, sir.
becomes integral of cos 2x is how much? Half sine 2x. Half sine 2x log sine x minus, now this is again half sine 2x, half integral sine 2x cot, um, this is cot 2x actually. No, this is cot x. Okay, sine 2x cot x dx, right? So this now becomes half sine 2x. Just let me know if you can't understand any step, because I have
Okay,
skipped
sir.
one or two
Okay,
steps here. Because I've skipped one or two steps here. Okay, minus half
okay, sir.
integral sine 2x is 2 sine x cos x by multiple angle formula, and you change cot x to cos x by sine x dx. Okay, so now this sine x and this sine x, they cancel. So what are you left with? Only you're only left with, and in fact this 2 and this 2 also cancel. Okay, so you get left with half sine 2x log sine x minus integral cos square x dx. How do you integrate cos square x? You change it to multiple angle formula. How do you change it to multiple angle formula? You know that 2 cos square x is 1 plus cos 2x. So half you can write, and you can write here 2 cos square x dx. So this is half sine 2x log sine x minus half of integral cos square x is 1 plus cos 2x dx. Okay, so this becomes is equal to half sine 2x log sine x minus half this. If you distribute the integral, you get half integral dx plus integral cos 2x dx, right? So you get half
Yes, sir.
sine 2x log sine x minus half. This becomes x plus half sine 2x plus c, right? So now we have evaluated the indefinite integral. Let us now evaluate the definite integral. Therefore, I is integral 0 to pi, integral 0 to pi cos 2x log sine x, cos 2x log sine x dx. And the indefinite integral, we have evaluated this to be half sine 2x log sine x minus half x plus half sine 2x. And this has to be evaluated within
Let's
the
see.
limits 0 to pi. Now put the put pi first. You get half sine 2 pi log sine pi
Yes, sir.
minus half pi plus half sine 2 pi. Okay, now put 0. So if you put 0, everything becomes 0, isn't it?
0. Yes,
Even
sir.
this becomes 0 because half sine 2 pi, the value is 0, right? Into log sine pi is also log
0.
1.
Log
This
1.
is sine pi is what? Sine pi is, yeah, sine is 0.
Yes, sir.
Yeah, this becomes 0. Because this becomes 0, everything is 0. So this entire expression actually becomes, is reduced to 0. So that's it.